Welcome to Math260. Our lesson today involves matrix multiplication. In our last lesson, we learned about matrix times vector, and so we'll build on that today with matrix times matrix. So here it is. By review, the product of the matrix A with the vector U exists only if the number of columns of A is equal to the length of the vector U. Suppose that A is m by n, that is, it has m rows and n columns. Then if U is an element of Rn, that is, a vector with n elements, then the vector V is the product of AU, where the ith component of V is the dot product of the ith row of the matrix with the vector U. That's why the number of columns has to be the same as the length of the vector, because each row contains the number of columns, or in this case m entries, n entries. And also notice that since we get one entry in the answer, one coordinate in the answer, for each dot product that we form, that's for each row of A, the size of the result is in Rm, because we have m rows. So here's a simple example where we have a 3 by 3 matrix, so we have to have a vector of length 3, and we form the matrix vector product as the dot product of the first row with the vector, giving the first element of the answer, the dot product of the second row with the vector, giving the second element of the answer. In this case, it's all 3 by 3, so we take a 3 by 3 matrix by a vector of length 3, we get a new vector of length 3. But let's build on that. Matrix times matrix. If the matrix A has m rows and n columns, and the matrix B is R by S, that it has R rows and S columns, then the product of the two matrices exists only if n equals R, that is, the number of columns of the first matrix is the same as the number of rows of the second one. When that's true, then the matrix C that we form as the product of the two matrices has dimensions m by S. It's as if we canceled out that middle dimension, where the ith column of the resulting matrix is formed by multiplying the matrix A by the ith column of B. And we know how to do that. That's matrix times vector. So we form the dot products of the rows of A with the ith column of B, and that gives me the ith column of the answer. In symbols, that's listed here. So let's look at it by way of example. It's easier to see. If I form the matrix multiplication between these two matrices, the first entry in the answer is the first row of the matrix A dot product with the first column of matrix B, and you can see the multiplication here. 3 times 4 plus 9, 19 times 1 plus 6 times 3, that gives me 89, and that's the first entry. To get the second entry in the first column, I go to the second row. So it's the second row of the matrix times the first column, and there's the arithmetic to give the answer 46. So this first column of the answer, 8946, can be thought of as the vector resulting from multiplying the matrix times the first column of B. To get the second column of the answer, we repeat the process, except we use the second column of the matrix B. So now it's first row times second column as a dot product, giving me 268, and then the second row times the second column as a dot product, giving me the arithmetic shows 107. So this is the idea. We simply extend our matrix times vector, where we do matrix times the first column, and that's the first column of the answer, matrix times vector as the second column, that gives the second column of the answer, etc. A very important point. Matrix multiplication is not commutative. This is our first real departure from our regular arithmetic. If A is m by n and B is n by r, then the product is m by r. But notice if I reverse the dimensions, BA, instead of AB, I do BA. BA is not even defined unless R happens to be M. If it is, then the resulting matrix BA is n by n, which in general has different dimensions than AB. But even if they're square matrices, that is, if both A and B are n by n, AB, the product AB, has the same dimensions as the product BA, but the answers are generally different, except in special cases. So here's an example. The matrix A, the matrix B, if I multiply A times B, then we can see the first answer would be 9 times 7 minus 7 times 6, and that's 105. Pause. Yeah, so because these are minus 7 times minus 6 is positive answer. So the first entry here is 105. But if I reverse the direction and multiply B times A, I'm going to take the dot product of 7, 12, 15 with the first column of A. That's 7 times 9 plus 12 times negative 6 plus 15 times 2. And if you do that arithmetic, you get 21. So even in the first entry, the answers are different. This is a big deal for matrices, even when they have the same dimension. When they're square matrices, AB is not BA. And that really messes up our algebra. For example, we would think that A plus B squared is the usual foiling, A squared plus 2AB plus B squared, but it's not. Why? Because if I use the distributive law carefully, I have A times A squared, and then A times B for the second entry. But now when I distribute the B, the first entry is not AB, it's BA, and then I get B squared. And since AB and BA are different, I don't get 2AB. This is just one example of how we need to use great care with matrix multiplication. The first example is something where the operation of multiply is not commutative. Okay, the identity matrix is a very special matrix. The n by n identity matrices has ones along the diagonal, the main diagonal, and zeros everywhere else. And it has the property that if A is m by n, m rows and n columns, then if I multiply on the right A times the identity matrix that's n by n, I get A back. And if I multiply by the m by m identity matrix, that times A also gives A. So it acts as the identity for multiplication. Let's look at an example worked out. So here's a general 2 by 2 matrix times the 2 by 2 identity matrix. The multiplication rule says the first entry is A11 times 1 plus A12 times 0. That's just A11. The second entry down here is formed by using the second row, A21 times 1 plus A22 times 0. So that gives me A21. And then to get the second column of the answer, I use the second column of the B matrix. So A11 times 0 plus A12 times 1. That gives me A12. And finally, A21 times 0 plus A22 times 1. That gives me, of course, A22, and that's exactly the same as the original matrix. So the identity matrix is important, and it behaves like 1 does for regular multiplication. Okay, we learned about the transpose of a matrix in previous lessons. If A has m rows and n columns, then the transpose has n rows and m columns. So that means I can always multiply A by A transpose because the second dimension of A and the first dimension of A transpose match up. I can also always multiply A transpose times A because the second dimension here matches the first dimension there. And as a result, A transpose is m by m, canceling out the middle n's, so to speak. And A transpose A is n by n because we start here, n by m times m by n, the middle dimension, m cancels out n by n. So generally they're not the same dimension, A transpose A and A transpose, but they're both square matrices. So here's an example. If A is 3 by 2, then its transpose is 2 by 3. Remember how we do that. To get the first row of A transpose, we take the first column of A. To get the second row of A transpose, we take the second column of A. So if I multiply A transpose, I'll have 3 by 2 by 2 by 3. That gives me a 3 by 3 matrix. And you should verify by hand that this is the resulting matrix. And if I form A transpose A, now I'm doing 2 by 3 times 3 by 2, so I get a 2 by 2 result. And again, you should verify by using the rules for matrix times matrix that we just went over that this is indeed the product. There's something special about these products. You may have noticed that they are symmetric about the main diagonal. Here's the main diagonal, and then we have 133, 133, minus 16, minus 16, 86, 86. That's not an accident. It turns out that A transpose, that product, is always a square symmetric matrix, and so is the product A transpose A. Okay, but some exercises. So here we're given two matrices and a vector. You're asked to compute AB, BA, A transpose, and B transpose U. So please pause the video now and work these exercises, and when we continue, you can review your solutions. Okay, so hopefully you paused the video and worked those exercises by hand and maybe verified with the calculator. Let's see what the answers are. If I multiply the matrix A, which is 2 by 3, by the matrix B, which is 3 by 2, I get a 2 by 2 answer. And just to verify, the first dot product that gives the first answer would be 4 times 9 minus 7 times 2 plus 8 times 5, and that indeed gives 62. BA, on the other hand, is a 3 by 2 matrix multiplied by a 2 by 3 matrix. The answer is 3 by 3. The first answer would be formed with the dot product 9 times 4 minus 1 times 15, giving me 21. A transpose, here's the matrix A, which is 2 by 3. A transpose is 3 by 2, so we get a 2 by 2 answer. And again, the first answer would be 4 times 4 minus 7 times minus 7 plus 8 times 8. And those are the answers here that you should check. And finally, if I multiply B transpose times the vector of variables there, I get 9 times x plus 2 times y plus 5 times z. That gives me the first result. And minus 1 times x plus 16 times y minus 1 times z gives me the second result. This is a 2 by 3 matrix times a 3 vector, giving me a vector in R2, a vector of length 2, as the answer. Okay, so hopefully this was a useful exercise for you. For homework, please download and study the notes for Lesson 9, Matrix Matrix Multiplication. In class on Monday, we'll get practice with Lessons 8 and 9, and we'll have a quiz on, actually it'll just be on Lessons 6 and 7. We won't do Matrix Matrix Multiplication quiz on Monday. And then for Wednesday, we'll look at matrix product behavior, an important lesson. That ends this video, so please look at this homework, and on Monday we'll review quickly Lesson 6, 7, and do some practice on 8, and then we'll have our quiz. And start.